Around 25 million years ago, an ancestor of yours had a tail. We do not know exactly what it looked like. We know only that it was an ape, that it lived in the warm Miocene forests of East Africa, that it climbed and ate fruit and slept in the high branches at night, and that, like every other primate alive at the time, it had a tail, a long one, almost certainly, used for balance, used for navigation along the upper canopy, used, as monkeys still use them today, to swat at flies, to signal to its kin, to keep warm in the cold hour just before dawn, and then, somewhere deep inside the cells of that ape, a small piece of foreign DNA, the kind of fragment that copies itself sideways through a genome, leaving its fingerprints across every chromosome in our species, slipped quietly into the middle of a single gene. The gene was called TBXT. The fragment was called ALU-Y. And the result, a generation later, was an ape born without a tail. We are the descendants of that ape. Every great ape that has ever lived has carried that mutation. So have you. So has every human child born today, every human child born tomorrow, every human child born for the millions of years ahead of us. And in the long, quiet stretch since, in the 25 million years between that single ape and the night you are listening to this, our bodies have been paying, very slowly and very quietly, for what that small piece of jumping DNA took from us. Tonight, we will spend 2 hours together inside the strange, unsettled story of how our ancestors lost their tails and what it has cost us to be born without one. There is nothing here you need to remember, no dates to test you on, no drama to keep you awake. We will simply move, slowly, through 25 million years of evolution, the inside of an embryo, the engineering of a vertebrate spine, the work of a single laboratory in New York that finally found the answer in 2024, and the long shadow of a mutation that wrote itself into your back, your pelvis, your gait. And, if you have ever woken with a sharp ache at the base of your spine, into your morning, settle in. Let the room grow quiet around you. We have a long way to walk together, and there is no need to hurry. Let me start by asking you to picture, for a moment, the base of your own spine. Most of us go through entire lives without thinking about it. The lower vertebrae, where the curve of the back tightens and ends. There is nothing dramatic there, nothing you can see, even when you are looking. It is one of those parts of the body that exists without commentary, without ceremony, without the listener ever needing to attend to it. But press a finger gently down through the muscle, between the upper edge of the buttocks, and you will feel, beneath the soft tissue, a small hard structure, a bony triangle, narrowing to a point. 3 to 5 vertebrae fused together over the years of your childhood, locked into a single shape by adulthood. It is called the coccyx, and though it is one of the smallest bones in the human body, it is, in some ways, the most peculiar bone any of us carry, because the coccyx is not really a bone in the normal sense of the word. The coccyx is, anatomically speaking, the empty socket where a tail used to be. The body is full of these quiet ghosts. The wisdom teeth that no longer fit our jaws, once useful for grinding the tougher plant matter our ancestors ate before fire and cooking softened their food, now extracted by the millions every year. The appendix, the small dead-end pouch in the gut, useful once for digesting fibrous leaves, now mostly notable for becoming inflamed and requiring removal in a small theater on a quiet weeknight. The auricular muscles, the small ribbons of tissue around the human ear, that in our ancestors swiveled the ear toward the source of a distant sound, and that, in most humans alive today, can no longer twitch at all. The erector pili muscles in the skin, which raise the hair on our forearms when we are cold, doing what once would have made our fur stand on end and trapped a layer of warm air against the body, and which now produce only goosebumps. There are even, deep in the tissue of the human shoulder and ribs, the faint residual fibers of muscles that other primates use to move the skin and dislodge insects. The body holds all of these gently, without comment. Like an old library that has stopped weeding the shelves, the anatomists have a word for them. They call them vestigial structures. The word comes from the Latin vestigium, a footprint, a trace, the mark of something else that has passed by. The body is, by this measure, full of footprints. Old structures that no longer perform their original function, kept on simply because there has been no urgent reason for evolution to remove them. They sit in us, harmless, occasionally inconvenient, holding the memory of older bodies than ours. The coccyx is the strangest of all of them. It is strange because we still have it. It is strange because it has not been allowed to vanish the way other vestigial structures sometimes do. It is strange because 25 million years after the structure it once supported was lost, it is still there at the base of every human spine, 3 or 4 little bones fused into a small triangle, performing as we shall come to a few quiet ceremonial duties that almost none of us ever notice. If you sit on a hard wooden chair without thinking, the coccyx is taking part of your weight. If you fall backwards onto a tiled floor, the coccyx is the bone that absorbs the blow, and the bone that may, after such a fall, ache for a year. If you lift a heavy object, or push something difficult, or hold a child, the coccyx is the small hidden anchor at the base of a network of muscles, the gluteus maximus, the levator ani, the coccygeus that hold up most of the weight of your body and most of the organs inside it. It is, in its quiet way, doing work. But the work it is doing is not the work it was originally designed for. It is the inheritance of a structure that, 25 million years ago, did something else entirely. This is a strange and almost beautiful thing to notice. The body is not a machine designed from scratch. The body is a long, layered, slightly improvised inheritance. Each generation has used the parts of the previous one as best it could. Each generation has had to make do with what came before. The coccyx is the most striking example of this because it is the most visible. It is the empty socket where a tail used to be, and it is still there, at the base of your spine, holding up the weight of you, 25 million years after the tail itself was last seen on any ancestor of ours. The story of how it got there, the story of why we lost the structure that the coccyx once supported, is the story we are going to walk through tonight. It is, in my opinion, one of the strangest stories in the whole of human evolution. And it is one we have only really understood in the last few years. The genetic mechanism was published in the journal Nature in February of 2024 by a team of researchers in New York. We will spend a chapter together inside their laboratory and inside the gene they finally identified. But before we get there, before we walk back through the millions of years of evolution to the moment of the loss, before we look at the lost forests and the lost ape and the small piece of jumping DNA that quietly rewrote our family tree, I want us to start much closer to home. I want us to start with the tail you yourself once had. It is hard to imagine, but every human being who has ever lived had a tail at one point. Not, of course, after they were born, but before, inside the womb, in the long, quiet weeks before any of us were ready to be seen. Every one of us grew a small, soft tail. It was not large. It would not have looked dramatic, but it was clearly a tail in every meaningful sense of the word. It had vertebrae, it had muscle, it had length. And then, some weeks later, our developing bodies very deliberately took it apart again. This was not a mistake. It was not an accident. It was a programmed event, written into the cellular machinery of our species, scheduled to happen at almost exactly the same moment in the development of every human child. At about 4 weeks after conception, the cells of the embryo begin to organize themselves into the tail bud. By the end of the 5th week, the tail is at its longest. It contains 10 to 12 developing vertebrae, complete with surrounding tissue. It accounts for roughly 1/6 of the total length of the embryo. If you could lift a 5-week-old human embryo gently in your hand, the first thing you would notice, and it would be hard not to notice, is that this tiny developing creature has a tail. And then, between the 6th and the 8th weeks of pregnancy, the body unmakes it. The cells at the tip of the tail receive a signal. 2 of the most ancient genes in vertebrate development, called Wnt3a and FGF8, are quietly turned down. The cells, deprived of their usual instructions to keep growing, begin to die. Specialized immune cells, called macrophages, move in and absorb the dying tissue. The body cleans up after itself. By the end of the 8th week, the tail is gone. The remaining vertebrae at the very base of the spine fuse, slowly, over the years that follow, into the small bony triangle we have already met. The coccyx. This is happening right now, in the wombs of every pregnant woman on Earth. It will happen in the womb of every pregnant woman who lives in the next 1,000 years. It is one of the most reliable, well-rehearsed, almost ceremonial moments in the development of our species. The body grows a tail, and then, a few weeks later, the body very carefully erases it. What is left behind, of course, is the coccyx and the strange genetic memory of a structure that almost came back. We do not have a tail because, around the 8th week of our development, our bodies did the work of making sure we would not have one. The mutation in the TBXT gene that we will spend a later chapter exploring does not prevent the tail from forming. It changes the fate of the tail after it has formed. It tells the body, in essence, to grow a tail and then, very precisely, to take it back, which is a strange way to make an animal without a tail. It is, when you stop and think about it, a stranger way to do it than simply not making the tail at all. But evolution is rarely as tidy as that. Evolution does not, on the whole, design things from scratch. Evolution edits old work. The simplest way for a tailed primate 25 million years ago to give rise to a tailless one was not to delete the entire ancient developmental program for the tail, a program that had been part of vertebrate biology for hundreds of millions of years before. That, the simplest way, was to keep the program and to add a single new instruction at the end. Grow the tail. The body still tells itself. And then, when you are nearly done, take it back. The consequences of doing it this way, of leaving the developmental program intact, and adding only the small amendment of late-stage erasure, are still felt. Occasionally, in the unusual cases that pass through obstetrics wards around the world even today, cases in which the erasure does not quite finish, cases in which a child is born with a small, soft protrusion at the base of the spine, an inheritance that the body had been told to put away. We will come to those cases gently in a later chapter, but it is worth marking here at the start of our long evening together that the genetic program for a human tail is not lost. It has been muted. It has been told very firmly to clean up after itself before birth, but the program is in every one of us still there. This is a peculiar inheritance. To carry in the cells of every embryo our species ever produces, the working blueprint for a part of the body that the body will, before birth, very deliberately take apart. To know that, somewhere inside us, the design for a tail is still being read out every time a new human is made, and then to know that this is normal, that this is what our species does, that every single one of us, for a few quiet weeks before we ever take a breath, has had a tail. It is a strange thing to think about. It is, I think, also a quiet way to begin a long story. The loss of the human tail is not only an ancient event, 25 million years away from us in the deep past. It is also, in a smaller way, an event that takes place every time a child is conceived. It is a piece of evolutionary history that the body has been carrying out, on schedule, every 9 months, for as long as our species has existed, which means that, in one sense, you have already lost your tail twice. Once, in the long forests of the Miocene, in the body of an ape you will never know. And once again, much more recently, in the soft and unobserved weeks of your own beginning, the first loss made our species what it is. The second is the small ceremony by which our species, every time, makes a new one of you. We will turn now from the inside of the womb to the outside world, to the wider primate family in which our ancestors lived, to the other branches of our family tree, the ones who did not lose their tails, and the strange uses to which they still put them, in the forests and grasslands and mangrove canopies of every warm continent on Earth. To understand why we are unusual, we need to look, for a while, at the cousins who are not. There are, alive on Earth tonight, more than 300 species of primate. Most of them have tails. The vast majority of them have tails. The tail is, for primates, the rule. It is the apes who are the exception. If you walked in some impossibly slow expedition through the warm forests of the world, from the temple courtyards of southern India to the rainforests of the Amazon, to the highlands of Madagascar, to the dry baobab woodlands of Central Africa, you would meet, at almost every stop, primates with tails, the little dawn chorus of long-tailed macaques in the temples at Lopburi, the colobus monkeys of East Africa, leaping between branches with their long white and black tails trailing behind them like banners, the langurs of the Himalayan foothills, the pattas monkeys of the Sahel grasslands, the proboscis monkeys of the Borneo mangroves, the little mouse lemurs of the Madagascan undergrowth, tarsiers, marmosets, capuchins, vervets, mandrills, each one of them, in its own way, with a tail. The tail in these animals is not a leftover. It is not a vestigial structure. It is not something the body has, for some old reason, forgotten to put away. It is a working part of the body, used every day. Watch a Japanese macaque cross a frozen branch in winter, and the tail follows behind it as a counterweight, a long, thin pendulum that adjusts itself, unconsciously, to keep the body in balance. Watch a colobus monkey leap across a 6-meter gap in the canopy, and the tail trails out behind it like the tail of a kite, doing exactly that work, stabilizing the leap, helping the animal land at the angle it needs. For smaller primates running along thin branches, the tail is a navigation tool. It is the difference, in many cases, between catching the next branch and falling. For larger primates working through dense vegetation, it is a signaling device, a punctuation mark for the body, raised in alarm or curled in calm. For the proboscis monkey, slowly digesting its difficult diet of leaves, the tail provides part of the long counterbalance the animal needs as it sits on a branch and waits for fermentation to do its quiet, internal work. For a few primates, a small special group, all of them living in the forests of Central and South America, the tail does something even stranger. It becomes a fifth limb: the spider monkey, the howler monkey, the woolly monkey, the muriqui. These animals all have what is called a prehensile tail, which means, simply, that the tail can grip. The end of the tail has been modified over millions of years of natural selection into a kind of dexterous tactile organ. The skin on the underside of the tip is hairless and ridged, almost like the skin of a finger. The muscles inside the tail are strong enough that the entire body of the animal, sometimes weighing 12 or 15 kilograms, can be supported by nothing more than the tail's grip on a single branch. A spider monkey, hanging by its tail, can use both hands to gather fruit, peel it, examine it, place it in its mouth. The tail does not let go. This, more than anything else in the primate world, is what is denied to us. We will never know, in the body of a human, what it would be like to feel a branch beneath the grip of a tail, to eat with both hands while suspended by a third limb, to navigate the high canopy with a fifth point of contact. The prehensile tail is the masterpiece of primate engineering. It is also a trick of the New World monkeys alone. Our own ancestors, in the Old World, never developed it. By the time some of our distant cousins, on a different continent, were perfecting the gripping tail, our own line of apes had already let the tail go entirely. Which brings us to the strange, almost embarrassing fact at the center of the primate family tree. The apes are the only primates without tails, all of them. Every species, the chimpanzee, the bonobo, the gorilla, the orangutan, the gibbon, the siamang, and us. 6 branches of the apes, 6 branches of cousins to us, and not one of them has so much as a stub. Each one of them has a coccyx, the small fused triangle of vertebrae we met in the last chapter, and not one of them has anything more than that. The chimpanzee scratching itself in the warm afternoon, the gorilla quietly chewing leaves in the wet forest, the orangutan high in the canopy with its long red arms, the gibbon swinging between the branches at a speed that would be terrifying to watch up close. Every one of them, our closest living relatives, is tailless, which is to say, the loss happened once. It happened in a single lineage, in a single ape ancestor, around 25 million years ago. And every descendant of that lineage, every great ape and every lesser ape, every chimpanzee and gorilla and orangutan and gibbon and human has carried the consequence forward, faithfully, ever since. The tail has not come back, not once, not in 25 million years of evolution. Despite all the strange paths the apes have taken, despite the gibbons swinging hand over hand through the canopy, despite the gorilla settling on the ground, despite the human standing fully upright on two legs and walking out of Africa, the tail has not returned. It went away in a single ancestor, on a single afternoon, hidden somewhere in the deep past, and it has not been seen since. This is unusual. Most of the body's lost structures eventually come back, in some form, somewhere on the tree of life. Whales, whose ancestors lost their hind limbs and walked on dry land for 30 million years before returning to the sea, occasionally produce calves with small back legs. Snakes, descended from lizards that had legs, sometimes show, in their embryos, the early stirrings of leg buds. Even the appendix, the famously vestigial pouch in the human gut, has been lost and re-evolved several times in mammals. Lost structures often re-emerge, here and there, when the conditions are right and the genetic blueprint has not been entirely overwritten. But not the ape's tail, not in 25 million years. The mutation that took it away has been, by some quiet measure, the most permanent decision our family tree has ever made. We will come to the question of why this loss, of all the losses, has been so absolute in a few chapters' time. For now, it is enough to notice the strangeness of the outcome. We are surrounded, as a species, by primates with tails. We are descended from primates with tails. The structure was useful for 200 million years of vertebrate evolution, and then, in our small branch alone, in one small group of climbing apes in the early Miocene, it stopped, and it has never come back. The Miocene. We have been moving towards this word, gently, since we began. Let us turn now to the time and place where the tail was lost. The Miocene was a long, slow epoch. It began about 23 million years ago and ended about 5 million years ago, which means that, when we say something happened in the Miocene, we are working with a window of nearly 20 million years. The world was warmer than it is today. The continents had nearly arrived at their modern positions, but not quite. India had finished colliding with Asia not long before, throwing up the young Himalayas. The Mediterranean Sea opened and closed and opened again. Africa, the cradle of the apes, was beginning to dry. Forests were being replaced, slowly and unevenly, by woodlands and grasslands. The world we see today, in its rough outlines, was being assembled. For the apes, the early Miocene was an extraordinary moment. The fossil record from East Africa during this period is dense with primate bones. There are at least a dozen species of early ape, possibly many more, scattered through the lake sediments and volcanic ash beds of what is now Kenya and Uganda. We do not know, even now, exactly how they all relate to one another. The branching is too fine and the bones are too fragmentary. But we can say, with some confidence, that the early Miocene was, for our distant ancestors, a time of flourishing. The apes, having only recently broken away from their monkey cousins, were trying out new ways of being primates, new body plans, new diets, new ways of moving through the trees. New, in particular, ways of living without a tail. One of the earliest of these apes, and the one we know best, has a name that I will mention now and that we will come back to often. The name is Proconsul. Proconsul was an early ape, alive in East Africa around 20 to 23 million years ago. Its bones have been found primarily on Rusinga Island in Lake Victoria, a small green island that has, over the course of the 20th century, given up an extraordinary number of fossils to the patient hands of a long line of paleontologists. The fossils were first described in the 1930s by an Englishman named Arthur Hopwood, who gave the new ape its mock classical name in homage to a much-loved chimpanzee performer in London called Consul. Proconsul, he wrote, meaning with the slight humor that paleontologists allow themselves before consul, before, that is, the chimpanzees we know today. Proconsul was not large. The smaller species would have weighed perhaps 10 kilograms, the larger, perhaps 80. They lived, as far as we can tell, in the forests of what is now East Africa, eating fruit and leaves, climbing slowly along the branches in the way that monkeys climb, on all fours rather than hanging beneath. Their teeth, in the way that ape teeth do, had a 5-cusp pattern, the so-called Y5, that they shared with all later apes and that distinguished them from monkeys. Their faces were forward-pointing rather than long-snouted. Their wrists and shoulders were already showing the early signs of the more flexible joints that later apes would develop, the joints that allow you, even now, to raise your arm above your head. And, most importantly for our story tonight, Proconsul did not have a tail. This is not a guess. This is not an inference from comparative anatomy. The tailbones, the small caudal vertebrae that, in any monkey of the same size, would have made up a third of the animal's length, are missing from the Proconsul fossils. They are not missing as in lost. They are missing as in gone. The base of the spine in the Proconsul fossils ends in something that looks remarkably like a coccyx, a small bony triangle at the base of the sacrum. The same shape, almost, as the bone we feel at the base of our own spine when we press a finger gently down, which means that, by the time Proconsul was alive, the tail was already gone. The mutation that took it away had already happened. The descendants of that single ape, the one in whose body the ALU-Y element had quietly slipped into the TBXT gene, had already begun to spread through the African forests. Proconsul, 20 million years ago, was already a tailless ape, which means, in turn, that the loss the moment we have been circling happened earlier, before Proconsul, before the divergence of apes and old-world monkeys. Probably between 25 and 28 million years ago, in a population of ancestral catarrhine primates living in the late Oligocene forests of Africa. We do not have the bones of that ancestor. We do not know its name, because we will probably never recognize its bones if we ever do find them. We know only that it lived, that it had a tail when it began, and that, in one of its descendants, a single mutation occurred. That descendant did not have a tail, and every ape that came after Proconsul, the great apes, the lesser apes, every one of our line, up to and including you, has been the inheritor of that one strange afternoon. It is one of the things I find most quietly extraordinary about evolution. The biggest changes, the ones that reshape entire branches of the tree of life, the ones that determine whether a future Earth will have great apes and humans on it or not, do not happen in moments of grand drama. They happen in single births, in single bodies, in afternoons that no eyewitness will ever remember. A small piece of DNA copies itself. It lands in the wrong gene. The body of the next ape born is a little different from its mother's. And the world, 25 million years later, is what it is. We should turn now to the laboratory in New York where the precise nature of that mutation was, finally, found. Because we have known for 150 years, since Darwin, that humans and other apes were tailless. We have known for half a century that the loss of the tail was an ancient event. But the genetic mechanism, the actual change in the actual gene that brought the tail down, was a mystery until very recently. It was a mystery that lasted, in fact, until the year before last. The story of how it was solved is, in some ways, my favorite chapter of this whole long evening. The story begins, as many stories of scientific discovery do, with an injury. In the autumn of 2019, a young Chinese-born graduate student named Bo Xia, working at the time in the laboratories of NYU Langone Health in New York, took a hard fall onto his coccyx. He was getting out of a taxi. The injury, as injuries to the coccyx so often are, was painful out of all proportion to its size and slow to heal. He spent the next several weeks unable to sit comfortably. And in that time, in the long uncomfortable days when even his desk chair was a kind of low-grade torture, he began to think about the small bone that was causing him so much pain. He began to wonder why, exactly, the human coccyx existed at all. He began to wonder why his body had a tailbone, but no tail. It is, in retrospect, a wonderful question. It is also a question that, despite a century of paleoanthropology, despite all the work on the Miocene apes and the divergence of the catarrhines, no one had ever really answered. Yes, we knew that the tail had been lost 25 million years ago, but how, precisely, had it been lost? What gene, what mutation? What change in the long, quiet text of the genome had taken away the structure that every other primate still has? Xia, in his pain and his curiosity, decided to find out. He was working in the laboratories of two senior scientists, Itai Yanai and Jeff Boeck. He had access, in those laboratories, to one of the most powerful tools in modern biology, the ability to look at the complete genetic code, the full DNA, of 140 different primate species side by side, the complete instructions for building a chimpanzee, the complete instructions for building a baboon, the complete instructions for building a marmoset, a tarsier, a slow loris, a human being, all laid out in long parallel rows of the four chemical letters A, T, G, and C, and ready to be searched, character by character, for whatever differences were hiding inside. He began with the obvious place. He began with the genes that are known, in mice and other animals, to control the length and the formation of the tail. There are about 140 such genes. They are the genes of vertebrate development. They are the genes that, in the body of every embryo, in every species with a backbone, are responsible for laying down the rear part of the spine, for forming the muscles that wrap around it, for shaping the structure that, in monkeys, will become a tail. Xia and his colleagues looked at all of them. Most of them were unremarkable. The coding regions of these genes, the parts that actually contain the instructions for the proteins they make, were essentially identical between monkeys and apes. Whatever had taken the tail away, it was not a difference in the protein-making machinery itself. But then they looked at one gene called TBXT. The Greek-rooted name was, in this case, ominously appropriate. TBXT had originally been called brachyury, a Greek compound meaning simply short tail. It had been named more than 100 years earlier, after a strain of laboratory mice in which a mutation in the gene caused the mice to be born with foreshortened tails. The link between this gene and tail length had been known for a long time. It was simply that no one had ever caught the gene in the act, in primates, of doing what its name suggested it did. When Shah and his colleagues compared the TBXT genes of monkeys and apes, the protein coding regions, the bits that actually make the protein, were almost identical. The ape version and the monkey version made the same protein in the same way. There was nothing wrong with the recipe, but the gene itself, the long stretch of DNA in which the recipe sits, was not identical. There were, in particular, two stretches of repetitive DNA sitting in what scientists call the introns of the gene. Introns are the parts of a gene that do not code for protein directly. They are spliced out of the gene's instructions before the protein is made. They are, in older textbooks, sometimes described as junk. They are not junk. They are doing quiet, important work of a kind that we have only really begun to understand in the last 2 decades. In the introns of the ape TBXT gene, in every ape's TBXT gene, every chimpanzee, every gorilla, every gibbon, every orangutan, every human, there sat a small piece of repetitive DNA called an ALU-Y element. It was about 300 base pairs long. It was inserted in the middle of the gene, and it was not present anywhere in any monkey. It was not in the macaque. It was not in the baboon. It was not in the colobus. It was uniquely, cleanly, perfectly present in every ape and absent in every monkey. Jeff Bogue, who is one of the senior figures in the field of human genome biology, would later describe the moment of recognition with unusual emotional clarity for a working scientist. It was like a lightning bolt, he said, in an interview with the journal Science. It was non-coding DNA that was 100% conserved in all the apes and 100% absent in all the monkeys. In a research field where the answer is almost always partial, almost always blurred, almost always the result of a long, careful weighing of probabilities, the answer to this particular question was, on inspection, absolute. The apes had it. The monkeys did not. Whatever this little 300-letter sequence was, it had something to do with what made an ape, and, more specifically, with what made an ape tailless. But finding a difference is not the same as finding a cause. The presence of an ALU-Y element in the ape's TBXT gene was, in 2021, when Xia first reported it in a preprint, a striking pattern. It was not yet a proven mechanism. To prove that this small piece of DNA was actually responsible for the loss of the tail, to prove that this particular 300 letters of code, sitting quietly in an intron, were the genetic signature of an event that had reshaped a whole branch of the primate family. Xia and his colleagues needed to show how the ALU-Y element was working. What they showed, when they finally worked it out, is one of the more elegant findings in modern molecular biology. It turned out that the ALU-Y element in the ape TBXT gene was not alone. There was, sitting some distance further along the same intron, another older ALU element, a small repetitive sequence called ALU-SX1, which had been there long before the ALU-Y arrived. Both ALU elements, the old one and the new one, were doing what ALU elements do, sitting quietly in their part of the gene, copies of a small ancient transposable sequence that had inserted itself long ago into the primate genome. But here was the strange thing. The new ALU-Y element, the one specific to the apes, had inserted itself in the reverse orientation to the older ALU-6-1 element. The two elements were almost identical pieces of DNA. They were facing in opposite directions. And when the gene was transcribed into RNA, the working copy of the gene that the cell uses to make protein, the two complementary sequences could fold back on each other and stick. The RNA, in this part of the ape TBXT gene, would tie itself, briefly, into a small lollipop-shaped loop, a stem of base-paired RNA, with a little ball of single-stranded RNA at the top. And that loop, Shia and his colleagues realized, was acting as a flag. When the cell processes its messenger RNA, the splicing machinery, the enzymes that cut out the intron sequences and stitch the protein coding bits together, reads the RNA as it goes. When it encounters the lollipop loop, it cannot pass through cleanly. It has to make a decision. And, in roughly half the cases, the decision it makes is to skip not just the intron, but also the exon next to it. Specifically, it skips exon 6 of the TBXT gene. The cell ends up making, in addition to the normal full-length TBXT protein, a shorter version of the protein with the 6th exon missing. This shorter version of the protein is called TBXT delta exon 6, and the body of the embryo, when it tries to use it, cannot build a tail. The result is exactly what the gene's old Greek name had predicted, more than a century before any of this molecular detail was understood. Brachyury, short tail. The protein that normally tells the developing embryo to build a tail had become, in the apes, partly defective. The tail bud forms. The vertebrae start to organize. But somewhere along the way, the cells receive an inconsistent signal. The full-length protein says one thing. The truncated protein says another. The tail does not finish growing. The macrophages move in. The body cleans up. To prove that this was the actual cause, that this exact mechanism was responsible for the loss of the tail, in apes, Shia and his colleagues did the next obvious thing. They built a mouse with the same change, using the modern gene editing technique called CRISPR-Cas9. They engineered a strain of laboratory mice that produced both the normal full-length TBXT protein and the same exon-skipped truncated version that apes produce. The mice that received the strongest dose of the truncated protein were born with no tail. The mice that received less of it were born with shorter tails. Some were born with kinked tails. The proportions varied with the proportions of the proteins. The mechanism was not just plausible. It was, at the molecular level, exactly what was happening in human embryos every day. When the result was finally published in the journal Nature in February of 2024, Shia's senior collaborator, Itai Yanai, gave an interview to the Science Press in which he described, in something close to wonder, what the team had found. "We're now walking on 2 feet," he said, "and we evolved a big brain and wheel technology, all from just a selfish element jumping into the intron of a gene. It's astounding to me. It is astounding. It is also, when you sit with it for a while, almost unbearably small. The thing that took our tails away, the thing that committed our entire family to a tailless body plan for 25 million years, the thing without which our species would not be the species it is, was not a glorious genetic redesign. It was not a clean switch in some grand control gene that had decided, for visionary reasons, to remove a structure that no longer served its purpose. It was a piece of jumping DNA, inserted in the wrong place, that happened to be facing the wrong way relative to its older neighbor, and that, when transcribed, folded itself into a small loop that confused the splicing machinery into making the wrong protein half the time, the loop, the lollipop. The wrong way ALU element in an intron of a gene with a Greek name that, by accident, perfectly described what it would later turn out to do. That is what made you what you are. We will turn now to the question of why. Of all the consequences this small piece of DNA could have produced, why was the loss of the tail one that the apes went on to keep? Why did natural selection, the slow and patient editor of all biological forms, allow this awkward little mutation to spread through an entire primate lineage and never undo it? The answer, when we look at it carefully, is that no one is entirely sure. This is one of those quiet, honest places in science where the textbooks tend to overstate what is known. Many books on human evolution will tell you, briskly, that the tail was lost because the apes adopted a particular kind of locomotion, brachiation, the swinging hand over hand through the trees that gibbons still perform spectacularly today, and that, in animals which swing through the canopy beneath the branches rather than running along the tops of them, a tail provides little benefit and considerable drag. The tail, the textbook says, was no longer useful, and so was no longer protected by selection, and so it went away. This is a tidy story. It is also, on closer inspection, not quite right. It is not quite right because Proconsul, the early ape we met a few chapters ago, was not a brachiator. Proconsul moved, as far as the bones can tell us, in a way that was much closer to the way Old World monkeys still move today. It walked along branches, on all fours, holding its body horizontally above the support. It was an above-branch quadruped, not a below-branch arm swinger. And yet Proconsul was tailless, which means that the loss of the tail happened before the apes settled into their distinctive way of moving through the trees. The tail went away first. The brachiation came later. Whatever drove the loss, it was not the loss of the tail's usefulness for swinging, because the swinging hadn't started yet. There is a second theory, which has more support among modern paleoanthropologists. It suggests that the early apes were beginning to adopt a more upright, vertical posture in the trees climbing trunks, rather than running along branches, sitting upright on stable supports, rather than balancing horizontally. In that more vertical, more upright way of climbing, the tail provides much less benefit. A monkey running along a thin branch needs the tail as a counterweight. A larger ape, climbing carefully up a thick trunk, does not. The tail, in this more vertical climbing pattern, is not particularly useful, and may even be a small liability. This is closer to the truth, perhaps, but it still does not fully explain why the tail did not simply shrink. Why did it disappear so completely, so quickly, and never come back? The most honest answer is that the loss of the tail may not have been driven by the gain of any new advantage at all. The single mutation in the TBXT gene was so dramatic and so global in its effects on the embryo that it may simply have been impossible for the early apes to undo it. Once the ALUI element was sitting in the intron, the splicing change was locked in. The body could not easily edit the change out. the next generation of apes, and the generation after that, and every generation since, was going to be tailless, whether or not it was particularly advantageous to be so. Natural selection might tolerate the loss, even if it did not actively favor it. The mutation, having arrived, was effectively permanent. And here we come to the central, slightly uncomfortable thought of this whole long evening together. We may be tailless not because being tailless is better. We may be tailless because of an evolutionary accident that, 25 million years ago, our ancestors could not undo. Our entire family tree, our entire line of cousins, the great apes and the lesser apes and the pre-humans and the humans, may have been shaped, structurally, by a small piece of jumping DNA that simply got stuck in a place from which it could not be removed. Everything that followed the upright climbing, the larger bodies, the eventual descent of our own ancestors from the trees and onto the African plains, the bipedal walking, the larger brains, the building of cities, the publishing of papers in the journal Nature about the question of why we have no tails, may have been built on top of and around an accident. This is not a comforting thought, but it has, I think, a kind of quiet beauty to it. The whole human story may rest on top of a piece of DNA that was, in evolutionary terms, an unforced error. We are not the inevitable result of a long upward climb. We are the descendants of an ape who couldn't put back what got broken. And we have been working, in our slow and quiet way, ever since, to build a body that can carry the consequences. The rest of this evening's story is mostly about that, about what the consequences have been, about what we, the descendants of the broken gene, have been quietly paying for ever since. We should turn, now, to the cost. The single most common cause of disability in the world, year after year, decade after decade, is the human lower back. It is a striking statistic. There are diseases in the world, terrible diseases, that take more lives. There are pandemics that move faster, and there are accidents that kill in single quick events. But for the slow, persistent, life-shaping cost of disability, of being unable to lift, unable to bend, unable to sit comfortably, unable to walk without pain, nothing in the human medical landscape comes close to lower back trouble. The latest figures, gathered painstakingly by the World Health Organization, estimate that, at any given moment, more than 500 million human beings are living with some form of lower back pain. 550 million people, roughly 7% of every adult on Earth. And that is only the figure for any given moment. Across an entire lifetime, the proportion of humans who experience meaningful lower back pain is closer to 9 in 10. The lower back, in our species, is the single most reliable place where the body breaks. No other primate lives like this. The chimpanzee in the wild does not, as a rule, suffer from chronic lower back pain. The orangutan does not throw out a disc lifting fruit. The gorilla, despite its enormous body, does not seem to spend any meaningful proportion of its life lying carefully on one side, cushioned by pillows, breathing slowly through a slipped lumbar disc. There are diseases of the joints in older apes. Of course, there is osteoarthritis everywhere in mammals, but the systematic, statistical, life-shortening epidemic of lower back trouble that humans live inside is, as far as we can tell, a uniquely human affliction, which is to say, it is the affliction of an animal whose ancestors lost their tails and then, much later, decided to stand up. The tail, in primates that still have it, is not just a structure for balance and signaling. It is also part of the structural geometry of the spine. The base of the tail is the back end of a long, gently curved beam of bone. The hips and pelvis sit in a quadrupedal animal beneath this beam, taking some of its weight. The shoulders sit at the front end. The whole structure is supported evenly and reasonably by 4 legs. The tail at the back is the long counterweight that helps keep the beam in balance. The animal can run, leap, climb, twist, all without much risk to the spine itself. It is a body plan that has been working more or less unchanged for 150 million years of mammalian evolution. It is a good design. When our ancestors lost the tail, they lost the back end of that beam. The pelvis, which had been sitting partway along, was now sitting at the very rear of the spine. The counterweight was gone. And then, a long while later, several million years later, in fact, our hominin ancestors did something even stranger. They tilted the whole beam upright. They began to walk on 2 legs. They took a body plan that had been designed over 150 million years for horizontal locomotion, and they pivoted the whole thing through 90 degrees. The beam that had been a horizontal arch, supported at 4 points, became a vertical column, supported only at the bottom. The lumbar vertebrae, the 5 large bones at the lower part of the spine, found themselves taking the entire weight of everything above them. Not the gentle distributed weight of a horizontal posture where the load is shared between 4 limbs, the full, concentrated weight of a torso and head transmitted directly downward, pressing through the soft cartilage discs between each vertebra and into the next bone below. It is a brave architectural choice. It allowed our ancestors to do extraordinary things, to walk for long distances on 2 legs, to free up their hands for tools, to carry food and infants over distances no other primate could match. The bipedal stance is the keystone of the human story, but it was achieved with a body that had not been designed for it. The body had been designed to balance horizontally, with a tail at the back. We took the body that an ape had inherited, and we stood it on end. And we have been paying for the geometric mismatch ever since. The lumbar vertebrae of the human spine, under this load, do their best. They are larger than the thoracic vertebrae further up. They are reinforced with more bone. They sit on top of one another in a graceful slight curve. The lumbar lordosis, which acts as anyone who has built an arch, knows to redirect some of the downward weight outwards into the surrounding muscles rather than straight down through the bones. The shape of the human back, the curve we recognize in every standing figure, is the body's small and elegant solution to the problem of standing upright on a spine that was never designed to do so. But it is only a partial solution. Over the years of working, lifting, sitting, twisting, sleeping awkwardly, falling, getting up again, the cartilage discs between the vertebrae compress, dry out, lose their flexibility, sometimes slip, sometimes herniate. The vertebrae themselves, under decades of load, develop small bony spurs, thicken at the edges, sometimes pinch the nerves running between them. The sacroiliac joint, where the lower spine meets the pelvis, is asked to absorb shocks for which it was never designed. The little ligaments around it stretch, sometimes tear. The pelvic floor, which the tail used to help anchor and which is now pulling double duty as a sling supporting the abdominal organs against gravity, weakens with age and childbirth. The muscles of the lower back, working hard to keep the column of bones upright, fatigue and spasm, all of these things are happening very slowly. In many of the people listening to this recording tonight, many of you are familiar with the small cost, the morning ache, the catch when standing up from a low chair, the careful turn made when twisting to reach for something on a back seat. The body remembers, in its own way, that it is an ape's body, working at an angle for which the ape's body was not designed. The body, in its quiet way, is paying. It would be one thing if the lower back were the only place where this geometry showed up. It is not. The cost of standing upright on a tailless ape's body is paid, in small installments, all over the body. The hip joints take more concentrated load than they were ever designed for, and slowly grind themselves down. The knees, which carry the entire weight of a standing human, and which have to lock and unlock with every step, develop arthritis at rates higher than any other primate. The arches of the human foot, which are unique among primate feet in being shaped for running rather than grasping, fatigue, fall, develop the problems we know as flat feet and bunions and plantar fasciitis. The pelvic floor, asked to support the heavy organs of the lower abdomen for an entire upright lifetime, weakens and prolapses. The veins in the legs, working against gravity to return blood to the heart, develop varicosities. The veins in the rectum, similarly working uphill against the upright stance, develop the small painful swellings we call hemorrhoids, which, again, are an essentially uniquely human affliction. No other primate routinely gets hemorrhoids. To get hemorrhoids reliably, you have to be a tailless biped. It is, in short, a long and quiet bill. We took the body of a tailless ape. We made it walk upright. And the body, in 1,000 small ways, has been sending us the invoice ever since. And then, just as we begin to make peace with this long, quiet inheritance, the laboratory in New York found one more thing. When Boscia and his colleagues had finished engineering their mice with the ape-style TBXT mutation, they noticed something that had not been part of their original question. The mice that had been born with no tails, or with shorter tails, were, on average, more likely than ordinary mice to have a particular kind of birth defect. A defect not in the tail at all, but further up the spine. A defect in the closure of what is called the neural tube. The neural tube is the structure in every vertebrate embryo from which the entire brain and spinal cord eventually develop. It begins very early in pregnancy as a flat strip of cells along the back of the embryo. Over the course of a few days, the strip rolls itself up like a long, thin scroll, fusing along the seam until it becomes a closed tube. The brain develops at the front end of this tube. The spinal cord develops along the rest of it. If, anywhere along the seam, the closure fails, if the rolling up is incomplete, if the fusion does not happen, the result is what we call a neural tube defect. In humans, neural tube defects affect roughly 1 in every 1,000 pregnancies. The most common is spina bifida, in which the closure fails over the lower spine, leaving a small opening that, in the most severe cases, can lead to paralysis below the level of the defect. The most extreme is called anencephaly, in which the closure fails so completely that the brain itself fails to form. Spina bifida, in particular, is well known. It can be screened for during pregnancy. It can sometimes be repaired surgically, even before birth. Folate supplements taken during pregnancy reduce the risk of it considerably. It is one of the conditions that obstetric medicine has, over the last 50 years, become quietly skilled at managing. What the New York researchers found in their mice was that the same genetic change that produced the short or absent tail also, in a small but statistically real proportion of the embryos, produced a higher rate of neural tube defects. The mutation that closed the tail down, in other words, did not do its work cleanly. It introduced, alongside the loss of the tail, a small but persistent risk of a much more serious developmental error further up the spine. It is not difficult to see why. The TBXT gene does not exist only to control the tail. It exists to control the entire posterior region of the developing embryo, the long strip of tissue from which the lower spine and the tail and the surrounding structures all eventually emerge. When you change the way that gene's protein behaves even slightly, even by introducing a partial truncated version of it alongside the normal one, you do not change only the tail. You change a small amount of everything that gene was doing, and one of the things it was doing in the early embryo was helping the neural tube close, which means if the mouse work translates to humans, and the researchers were careful to point out that this still needs further confirmation that part of the cost of being tailless in our species is paid not by adults with sore backs, but by an unknown small fraction of unborn children every year, in the failure of a closure that, in our tailed cousins, happens cleanly. The cost, in other words, is still being paid. Not just historically, in the long inherited problems of bipedal posture, but now, today, in the present tense, by the children of our species who never quite finish forming. It is a sober thought. It is one of those places where the otherwise rather magical seeming story of evolution turns, briefly, into something more difficult. The mutation that took the tail away gave us, in exchange, the body plan that allowed us to become what we have become, but it did not give it for free. It charged a small, ongoing fee, and the fee is still being collected. Jeff Boker, in the same set of interviews after the publication of the paper, put it as simply as it could be put. It may be a sort of unintended consequence, he said, that TBXT deficiency gives you a short tail, but it makes it more likely that you don't get that complete neural closure. That is the language of an honest scientist, trying not to overstate. But the underlying fact is something heavier than that. The bargain that gave us our shape was not a clean one. There was a small dark cost folded into it, and every generation of human beings, including this one, has paid a fraction of that cost in the lives of children who never made it to be born, or who were born with the partial closure that the older program of vertebrate biology has, in our line, become slightly less reliable at completing. We will move now to a related and much rarer kind of evidence that the developmental program for a tail still lives, dormant, inside our species. For as long as there have been medical journals, there have been occasional reports, here and there, every few years, of human children born with tails. This is a sentence that I want to say carefully, because it is one of those facts in human biology that has often been mishandled. There are stories, going back into the 19th century, of so-called tailed humans. Some of those stories were exaggerated. Some were the work of sideshow exhibitors who attached prosthetic tails to perfectly ordinary children for the sake of a paying audience. Some were the result of medical misclassification of small lipomas or skin tags being confused for genuine vestigial structures. The history of the question is, in places, not a noble one, but the genuine cases exist. They have been documented since at least the late 19th century in the proper medical literature, in case reports in journals of pediatrics and obstetrics around the world. They are rare. The total number of properly documented cases across the whole history of modern medicine is somewhere between 40 and 100. Some reviews put it lower, some put it higher. Doctors classify them carefully, because the classification matters very much for the question of how to treat them. The basic distinction is between what is called a true vestigial tail and what is called a pseudo-tail. A true vestigial tail is what it sounds like. It is the result of an incomplete erasure of the embryonic tail bud. The structure is soft. It is covered in normal skin. It contains no bone, no cartilage, no spinal cord. It contains, at its core, a small amount of fatty tissue, some connective tissue, sometimes a thin core of striated muscle, sometimes a bundle of nerve fibers, sometimes the small pressure-sensing structures called Pacinian corpuscles. In the rarest cases, the tail can twitch, not in any controlled way, but reflexively, in response to certain kinds of touch. The longest documented true tail in modern medical literature was about 13 centimeters. It was on a child in southern India. The doctor who removed it described, in a quiet way, the small movement the tail made just once when he picked it up. A pseudo-tail is different. A pseudo-tail looks like a tail, but it is not the residue of the embryonic tail. It is something else. It is, often, an extra projection of the lower coccyx, or a lipoma, a benign fatty growth, or, in the most concerning cases, the surface marker of a much more serious developmental problem in the underlying spine. Children born with pseudo-tails are not, on the whole, in trouble because of the projection itself. They are sometimes in trouble because of what the projection is sitting on top of a tethered spinal cord, an open neural tube, an inner failure of the kind we have already discussed in this evening's chapter on neural tube defects, which is why, when a child is born today with a small caudal projection, the first action of the medical team is not surgery. It is imaging, an ultrasound, an MRI, a careful look at what lies underneath. The distinction between a true vestigial tail, which can usually be removed safely, with no consequences for the child's later life, and a pseudo-tail, which may indicate a serious underlying defect that needs careful and considered treatment is, in modern obstetric practice, one of the most important first questions to be answered. The true vestigial tails, when they occur, are not a sign of anything wrong. They are, in a strange and rather quiet way, a sign of something extraordinarily right. They are evidence, in real living human bodies, that the developmental program for a tail is still inside us. The blueprint has not been deleted. 25 million years after the ALU-Y element slipped into the TBXT intron, the body still knows how to make a tail. It usually does not. It is meant not to. The system is meant to grow the tail bud and then erase it, on schedule, by the 8th week of pregnancy. But once in every several million pregnancies, somewhere on Earth, the erasure is incomplete. The body builds the tail and then, for whatever reason, does not put it away, which is, when you sit with it for a moment, an astonishing thing to know about our own species. We carry, In every fertilized egg, the working blueprint for a structure that is several 100 million years old, that our direct ancestors lost 25 million years ago, that has not been a useful part of the body of any human being for longer than the entire history of mammals on Earth, and that, very rarely, will turn up again. The structure is still there, dormant. The instructions still exist. The body could, in principle, build one. The body is told, very firmly, not to. But occasionally, in the soft, uncertain weeks of early pregnancy, the order does not get carried out, and a child is born with a small, soft tail at the base of the spine. Most of these children grow up entirely normally. The tail, when it is a true vestigial structure, is removed in a short surgical procedure, and the child has a small surgical scar where the tail used to be. The scar is, in some sense, the visible reminder of what the rest of us also carry. Just without the visible reminder, we all have the scar on the inside. We all have the empty socket of the coccyx and the long erase program for the tail that has, so faintly, almost entirely disappeared from us. The children with tails are simply the cases where the erasure was a little less complete. It is, I think, a strangely tender thing to know. The body is not a finished design. The body is an ongoing project, working with materials that are very, very old. Sometimes, in the soft work of building a new human being, an older instruction surfaces. Sometimes the body remembers what it is meant to forget. We should turn now from these rare cases in their quiet medical books back to the strange way that all the rest of us, every day, do something that no other primate species does. We walk upright. We walk on two legs. And the way our bodies do this is, in its own way, the central anatomical consequence of the loss of our tails. The human walk is one of the strangest gaits in the animal world. It is so common to us, so ordinary, so much the background of every day, that it is hard, sometimes, to see how unusual it really is. But step back, just for a moment, and watch a person walk down a street. The body, balanced on a small surface area at the bottom of two long legs, swings smoothly forward. The hips rotate slightly with each step. The arms swing in countertime to the legs, balancing the rotation of the torso. The head stays remarkably still, despite the fact that everything beneath it is moving in coordinated waves. The whole apparatus is supported at any given moment in the gait cycle on a single foot, the foot whose entire purpose is to take, briefly, the entire weight of the body before passing it to the next foot. No other animal walks like this. The chimpanzee, when it stands upright, which it can do, but only for short distances, looks awkward. It rolls. It struggles to balance. Its legs are short relative to its torso. Its hip joints are not aligned beneath the body in the way ours are. Its pelvis is shaped, fundamentally, for quadrupedal locomotion. The chimpanzee can walk on two legs. It can do so for surprisingly long stretches when it needs to. But the quadruped is its proper form. The biped is something it puts on, briefly, like a costume. It is not what it was made for. We were made for it, not by some grand design, of course, by a long, slow, 2 million-year process of selection working on the bodies of our hominin ancestors in the African savannas, on the anatomy of pelvic bones and femur angles and foot arches and lumbar curves and the orientation of the great toe and the shape of the ear's vestibular system. The bipedal walk we now perform without thinking is the result of one of the longest and most committed body redesign projects in the entire history of the mammals. And it could not have happened on a body with a tail. This is the deepest connection between the loss of our tail and what we have become. Bipedalism, for an ape, is much harder if you also have a tail behind you. The tail's natural role in monkeys is to hang out behind the body, balancing it. It is a counterweight. When you stand a four-legged animal up on two legs, the natural place for the tail to point is downward and slightly back, like the mast of a small sail. And the natural consequence is that the tail interferes with the new posture. It catches on the ground. It pulls the center of gravity backwards. It changes the balance of the standing animal in ways that are, on the whole, unhelpful. If you wanted to design a primate that could stand upright comfortably for long periods, you would, if you were starting from scratch, leave the tail out, which is, in a sense, what evolution did, or rather, what evolution had already done 20 million years before our ancestors ever stood up. The tail had already been gone, in our line, for a very long time when bipedalism became a serious possibility. The mutation in TBXT had already cleared the geometric way. The pelvis, the lumbar spine, the muscles that anchored the rear of the body, all of these had been, very slowly, redesigned around a tailless animal. By the time the early hominins began to stand upright, the body that had been left to them by their tailless ancestors was, in a quiet way, already half prepared for the posture they were about to adopt. This is one of those moments in evolution where it is worth slowing down and noticing how indirect, how patient, how unintentional the connections between things really are. 25 million years ago, a small piece of jumping DNA disrupted a single gene in a single ape. That ape and its descendants became tailless. Over many millions of years, the bodies of those tailless apes slowly redesigned themselves around the absence. The muscles of the rear of the body found new things to do. The pelvic floor took on the work of supporting the abdominal organs. The lumbar spine adopted its slight curve. The bodies became, in a small way, more vertical, more upright in their climbing, more accustomed to balancing without a tail at the back. And then, a long while later, perhaps 15 million years later, in a small offshoot of the line, in the bodies of one particular kind of African ape, the slight verticality became more than slight. The animal began to stand. The weight of the torso, already supported by a tailless pelvis, was now lifted entirely off the ground. The legs lengthened, the pelvis broadened and shortened, the lumbar curve deepened, the foot, which in other apes had been a kind of soft hand for grasping branches, became a stiffer paddle for striking the ground. The head moved, over the centuries, into balance directly above the spine. The body of an ape, which had been edited for tens of millions of years around the absence of a tail, was now edited again, around the new posture of standing upright on two legs. The second editing rests on the first. We could not, in any plausible scenario, have stood up if we had still had tails. The bipedal walk that you perform every day is built, structurally and historically, on top of the loss that took place in the body of one ape 25 million years ago, when an ALU element fell into the wrong gene, which is why, when we feel the cost, when the lower back aches, when the knees protest, when the pelvic floor weakens, when the lumbar disc slips, we are, in a sense, not paying for one inheritance but for two. We are paying for the original loss of the tail and the body's slow improvised redesign around it, and we are paying for the second, much more recent decision to stand. The two costs are folded into each other so completely that they cannot be separated. We are an animal whose body was designed, in part, around the absence of one structure, and in part, around the addition of a posture, and the design has worked well enough that we have inherited the planet, but it has not worked perfectly. There are gaps, there are mismatches, there are places in our anatomy where the patches show. The ache in the lower back is the body's quiet way of saying that it remembers. We have been speaking for several chapters now in the language of biology, of genes and bones and embryos, and the slow patient editing of bodies across deep time. We should, before this evening ends, turn briefly to a quieter question. A question that does not belong to biology at all, but to the human imagination. Why is it that almost every culture in the world, from the medieval villages of Europe to the temple cities of southern India to the small mountain shrines of Japan, has imagined its monsters and its devils and its supernatural messengers with tails? It is one of those things, once you notice it, that you cannot easily unnotice. The imp of the Western devil tradition has a tail. The dragon of the Eastern myths has a tail. The kitsune of Japan, the fox-like spirit beings of folklore, are recognized by their tails, and the more powerful the spirit, the more tails it has, until the most powerful of all, the nine-tailed fox, has 8 more tails than the body of any actual fox could ever bear. The Naga, the serpent-bodied beings of Hindu cosmology, are tails, entire tails ending in human torsos, or tails ending in human heads, but tails essentially. The mermaid is a tail joined to a woman. The minotaur, in some old depictions, has a small bovine tail at the back. The little demons in the corners of medieval Bibles, in the choir stalls of Gothic cathedrals, in the painted manuscripts of Romanesque monasteries, are festooned with tails of every shape, forked, barbed, scaly, smooth. The pattern is not subtle. The supernatural beings of the human imagination, again and again, across continents and millennia, are marked by the one thing the human body does not have. They have tails. We do not. They are visibly, recognizably, not human. And the tail is, in this iconography, the most efficient single way to say so. It would be too neat, perhaps, to say that this is a memory, to say that, somehow, the human imagination still recognizes what it has lost, and so when it imagines the strange and the powerful and the not quite human, it adds the structure that we, as a species, gave up. There is no good biological evidence that any cultural memory of that kind could survive 25 million years. The mutation that took our tails away predates not just our species, not just our genus, but the entire mammalian lineage that gave rise to all of the apes. Whatever lost the tail predates anything that could have remembered it, but it would be too quick, also, to dismiss the pattern as a coincidence. The human imagination is not random. It tends, when it reaches for the alien and the supernatural, to reach for the same kinds of things: wings, on beings that should not have them; horns, on creatures that should not; tails, on bodies that should not. The recurrence is not a memory of the lost. It is, perhaps, more interesting than that. It is, perhaps, the human imagination noticing what is missing in itself and using the absence as a marker for everything that it is not. In the Hindu tradition, the cosmology has, in places, an even more delicate relationship to the tale. There is a story told in the old Puranic texts of the demon Svarbhanu, who tried during the great churning of the cosmic ocean to steal the nectar of immortality. The gods, recognizing his deception, had him beheaded by the great discus of the god Vishnu, but the nectar had already passed his throat, so both halves of his body became, separately, immortal. The severed head became Rahu, a roving cosmic figure who chases the sun and moon across the sky and, when he catches them, briefly swallows them. This is the cause, in the old astronomical tradition, of solar and lunar eclipses. The severed body, ending in a long serpentine tail, became Ketu, a counterpart to Rahu, also chasing the sun and the moon, also a cause of eclipses, but with a very different symbolic flavor. Ketu, in the Vedic astrological tradition, is associated with the absence of attachment, with detachment from the material, with the spiritual realm, with intuition, with liberation from worldly desires. He is, in the old language, the ascetic, the one who has no head, and therefore no rational mind, and therefore no entanglement with the small concerns of daily life. He is a tail without a body. A tale that has, in this elegant cosmological turn, come to mean spiritual freedom. It is, when you sit with it, almost the opposite of the medieval European reading. In the European tradition, the tale is the mark of the lower, the bestial, the not yet human. In the Vedic tradition, the tale can be the mark of the higher, the freed, the no longer merely human. The same anatomical feature, the same absence in our own bodies, has been read in two opposite ways by two different cultural traditions. In one, it is what we have risen above. In the other, it is what we are still trying to ascend toward. The truth, of course, is that the tale is neither of these things. It is a structure that some of our distant cousins still possess, and that we, by an evolutionary accident 25 million years ago, do not. The cultural meanings layered over it, the demonic, the spiritual, the alien, the lost are our own work. They are the ways we have made sense of the absence. But the absence itself is older than any of those readings. The absence began in a single Miocene afternoon, with a piece of jumping DNA falling into the wrong intron of the wrong gene. Everything else, the imp, the kitsune, the naga, the devil, the figure of Ketu in the Vedic sky, the mermaid in the wave is what the human imagination has done. Since, with what its body forgot, it is one of the small, quiet beauties of being human, I think, that we cannot leave the absence alone. We keep finding ways to put a tail on the imagined things that surround us. The animal that lost its tail 25 million years ago is, even now, still drawing them onto its monsters and its gods, as if some part of us, somewhere, has not forgotten. We should turn, in this last chapter, towards the closing thought of this whole long evening together. The mutation that took our tails away is roughly 25 million years old. That is, in the slow geometry of evolutionary time, an enormous span. There have been ice ages since then. There have been the rises and falls of entire genera of mammals. The continents have shifted. The Mediterranean has dried out and refilled. The grasslands of Africa have spread, and our own line of ancestors has emerged from the forests, walked upright, made tools, painted caves, built villages, cleared land, written books, sent messages across continents at the speed of light, and lifted, briefly, a small piece of metal off this planet and onto another. All of that, every last bit of it, has happened on top of an inheritance that began with a piece of jumping DNA. And that inheritance is locked. There is no path back from it. The ALU-Y element is sitting, right now, in the TBXT gene of every great ape on Earth, including every human being currently alive and every human being who will ever be born. It cannot be removed. It is too embedded, too tightly woven into the developmental program of our species to be undone by any reasonable evolutionary process. We are, as a species, committed. We will be tailless for as long as our line lasts. What that line has done with the inheritance is, for an animal that is sometimes inclined to think rather highly of itself, worth a moment's reflection. We took the body of a tailless ape and we redesigned it for vertical living, and we paid a small bill in the form of slipped discs and lower back pain. We took that vertically living tailless ape's body and we redesigned it again for upright walking, and we paid a larger bill in the form of childbirth complications and pelvic floor weaknesses and varicose veins. We took that upright walking tailless ape and we used its freed up forelimbs to make tools, to handle fire, to weave fabric, to write language, to count numbers, to look up at the night sky and ask what was up there. None of that would have happened in any obvious counterfactual if we had still had tails. We are, in some unsentimental way, the children of the broken gene. It is a strange thing to know about oneself, to know that the smallest events in the deep past, the events that no eye saw, that no record marks, that lasted for one afternoon in the body of one animal whose name we will never know, can ripple forward, faithful and unreversed, into the body that is, right now, listening to a voice in the dark, the body that is, right now, breathing slowly, growing tired, turning over, drifting. That body, your body, is the inheritor of a single quiet event in a Miocene forest 25 million years ago. The mutation is still inside you. The mutation will be inside the children of your children and the children of theirs, and the millions of children of our species who will be born long after this recording has stopped being heard. The coccyx is at the base of your spine. You can press your finger to it, if you would like. 3 small fused bones, the empty socket where a tail used to be. The little inheritance of a forest none of us will ever see, of an ape none of us will ever meet, of an afternoon when, somewhere in the warm shade of an early Miocene woodland, a single new piece of DNA fell, very gently, into a single old gene, and the world, 25 million years later, became what it is, in the embryo of every human being conceived tonight in every womb, on every continent, in every house with a sleeping mother, a small tail is forming. By the 8th week of those pregnancies, the tail will be gone. The body will have, on schedule, taken it back. The macrophages will have moved through the tissue. The cells of the tip of the tail will have died on cue, and the small bony remnant at the base of the spine will have begun the long, slow fusion that will, by the time those children are grown, be the coccyx of the next generation. This happens, gently and unobserved, every day. It will keep happening for as long as our species exists. We are, all of us, the descendants of an ape that lost its tail. We carry the loss in our embryology, in our spines, in our gait, in the small daily aches of our adult lives, in the strange persistence of the tale in the monsters and gods of our cultures, in the rare children born with the small, soft remnant that the body, that one time, did not put away. We are not finished. The body is not finished. Evolution is still working, very slowly, with the materials it has been left. But for tonight, our long walk through this story is at its end. The forest is quiet. The Miocene is far behind us. The little ape that began all this, in whose body the Alu-Y element first found its place, has been gone for 25 million years, and we will never know what it looked like, and we are its descendants. The tail, in the long backward chain of our ancestors, is the thing that left. Thank you for spending these hours with me. There is no shame, of course. If you have drifted off some way back, if a chapter or two has passed without your hearing it, because the words will still be here when you come back to them, and the body that has been listening, whether or not the mind has stayed with it, has done its own quiet work in the dark. The breathing, the slowing, the small loosening of the muscles that keep the spine of a tailless ape upright through the day, all of that is the body's own quiet response to a quiet voice in a quiet room. And all of it is, in its small way, an inheritance, your inheritance, our inheritance, the inheritance of a long line of apes who lost something 25 million years ago and who learned, slowly, to live without it. Sleep well. The night is long. We will be here when you wake.